Hello and welcome to lecture number 15. This is the last lecture from chapter 3, which is the Schrodinger equation and its application in some simple systems. Okay, so we have been talking about the uncertainty. Okay, so uncertainty to measure position, which is defined as sigma x, which is the square root of the variance. And this is basically defined by this quantity. Okay, so we are familiar of this expression and we have already seen this. So similarly, the same thing we can write for the momentum in one dimension, sigma px, which is equal to this. Okay, good. And in our last class, we have determined the average position of a particle, free particle in a one-dimensional box, and it came out to be a by 2. That means the particle on an average is expected to be exactly at the center, means the mean position is at the center of the box, a by 2. So our today's job is to find out the entire expression of the uncertainty in position and the entire expression for the uncertainty in the momentum. Okay, so let's work it out. So therefore, today we will start with the average of x square. Okay, so by definition, the average of x square is defined as integration 0 to a, and we have psi star x by definition multiplied by the x square as an operator, and it is operating on psi x dx. All right, now this is true if psi x is an imaginary quantity, so we can have the psi star x and psi x, but we know for a free particle in one-dimensional box, psi x is a real function. So for this we can safely write this expression. All right, so that means x square can act as a multiplicative manner and multiplied by psi star x psi x, which becomes as the mod of or absolute value of psi x and then whole square. All right, so the question is, what is the value of this integral? So further we can definitely write 0 to a x square, and for this one we have already found out that the 2 over a should be here, and then sine square n pi x by a dx. All right, so this should give us the final value of the integration. The question is, what is the final value? So the final value would come out from some standard integral and some standard calculation. So to save time, I'm not going into the details of the calculation, but I will be just writing the final results. Okay, so the final results comes out to be something like this. It comes out to be a square divided by 3 minus 2a square divided by 4 pi square n square. All right, so this is our value of x square, but our goal is to find out sigma x. So we quickly clean up the board and let's start with the expression of let's derive the complete expression of sigma x. So let's do that. So we start again. We just have rewritten the expression of x square average here minus average of x whole square. So the average of x we already found out to be a by 2. So the square of that means a square by 4. So we can rewrite it as root over of. So we can take x square divided by 4 pi square n square common. And if we do that, we get another expression inside the bracket, and the value comes out to be pi square n square divided by 3 minus 2. Okay, so this becomes equal to, we can take this value out of the square root, so it becomes a divided by 2 pi n, and then square root of pi square n square divided by 3 minus 2. So this becomes our final value of sigma x. Alright, so now we are determined to find out what is the value of sigma px. Okay, so definitely in order to find out sigma px, we need to find two things, that is the average of px and average of px squared. So we need to find these two and this. Okay, so we start with this value, so average of px. Okay, so like the previous definition, we again have to rewrite the definition of average of px. So the average of px stands for 0 to a, okay, chi star x, and the momentum operator px. Okay, so px cap, so this basically this is px cap chi x dx. So now we have to fill in the values for chi x and px cap. What is chi star x? Definitely root over of 2 by a sine n pi x by a. Now the px cap, it stands for, remember, minus I h cross dtx. Okay, so this, we can put a bracket over here. So this is getting operated on, once again, root over of 2 by a sine n by x by a dx. Alright, so we have this whole integral over there written. Okay, so we have to find out the expression for this. So we can rewrite is equal to, so you see, this is the first derivative of root over of 2 by a sine n by x by a. So if I take that and all the constant terms would come outside, so if everything comes outside, so we have 2 divided by a, and another a should be coming out, a square, and then we have a minus I, and then we have n pi. So minus I to n pi divided by a square, and again the integral 0 to a sine n pi x by a multiplied by the first derivative of cosine n pi x, that sine n pi x, that means cos n pi x by a dx. Okay, so the question is, what is the value of this integral? So if you work out this value 0 to a sine n pi x by a cos n pi x by a dx, this integral, fortunately or unfortunately, comes out to be 0. So therefore the entire integral value comes out to be 0, meaning that the average momentum of a free particle in a one-dimensional box becomes 0. So that is something very significant, and the question is it expected or unexpected? So any physical significance of the average momentum becoming 0, I would get back to the point at the end of this lecture. But let's continue whatever we are doing. So we are trying to find out sigma px. So one of the component was average px, and we found out that it is 0. So let's figure out what is the value of, so this we have determined 0, and let's find out what is the value of px squared average. Okay, so let's clean up the board and work it out. Before we proceed, there was a mistake, so I forgot to take out this h cross here. So h cross would come here as a constant, so that was slight calculation mistake, pardon me. So that is the correct expression. So now let's continue once again. So coming back, we are here in a process of finding sigma px, so which is root over of px square average minus average of px whole square. Okay, and we have already found out that this is 0, so this becomes is equal to simply root over of px square average. Okay, so here now we want to find the average of px square. So according to our definition of average value, so we have to write 0 to a psi star x px square cap, so that is the corresponding operator, psi x dx is equal to, so we have to write the function that is root over of 2 by a sine n pi x by a, and then we have the px square. So remember, what is px? Px was minus ih cross ddx, so therefore px square means simply the square of this operator, so that means minus I whole square h cross, okay, square d2 dx2, simple. So here once again, so we write this quantity that is minus I whole square h cross square d2 dx2, and then again root over of 2 by a sine n pi x by a dx. All right, so this is the whole expression of the big integral. So therefore what we can do is we can take out these constant values, so we can take 2 over a, all right, and then I square is equal to minus 1, so minus I whole square means positive 1, so it comes out as 1 h cross square. Okay, and then we have this n pi x by a, and we are taking the double derivative, so n pi over a would come out twice, so it would come out as n square pi square divided by a square. All right, so it would simply come out to be like this, and then we have the integral 0 to a sine, you see this is sine square n pi x by a dx. Okay, so because the first derivative of sine is cos, and then again another second derivative of cos is positive sine. Okay, so this is the integral value now, so is equal to, now this portion is already known to us. Remember, during the normalization of wave function we have dealt with this integral, and we know that this value was a divided by 2. Okay, so this part is equal to a divided by 2. So if we do the everything here once again, so we can write 2 over a h cross square multiplied by n square pi square divided by a square multiplied by a divided by 2. So we can cancel out few terms, and therefore we are left with n square pi square h cross square a square. Okay, so this is the value of the average of px square. So therefore we still need to find the value of sigma px, which is the square root of this. So simply now our life becomes easier. So sigma px is now the root over of n square pi square h cross square a square. All right, so therefore we take the positive square root of this value, so this becomes n pi h cross divided by a. So finally we got our value sigma px. So we have already got our value for sigma x, so now we have got sigma px. So now we see that how these two uncertainties are related with each other. So let's clean the blackboard and freshly do it. Okay, now let's see how these sigma x and sigma px are related with each other according to Heisenberg's principle. So the sigma, the another significance of this is the spread of distribution around its mean value. That means it's the uncertainty in measurement, basically standard deviation. So therefore sigma x is the uncertainty in position, which is simply delta x, uncertainty in measuring the position, and which is equal to the value that we have already got. So we can write out once again a divided by 2 pi n root over of pi square n square divided by 3 minus 2. Okay, so that's the value we have just got from the calculation, and sigma px that we have got so far is n pi h cross divided by a. All right, so we by taking the positive square root of it. So this is the uncertainty of momentum. That means this is delta px, the uncertainty in the measurement of the momentum. Okay, so let's take the product of sigma x and sigma px. So this product means we are taking the product of the uncertainty of measurement of position and the uncertainty of measurement of momentum. Okay, so if we take the two product, let's see what we get. We get a divided by 2 pi n root over of pi square n square divided by 3 minus 2 whole multiply by n pi h cross divided by a. Now we can see that these a parts, n and pi parts cancel out, and what we are left with is this h cross divided by 2 within bracket root over of pi square n square minus divided by 3 minus 2. Okay, so that's our final expression. Okay, so now you see that let's take a look at this fraction over here. Okay, so this is pi square, so pi is what, 3 point something. Okay, so pi square means, so pi is greater than 3, so pi square means it is greater than 9. So some value greater than 9 divided by 3 is definitely, it is greater than 1. Okay, sorry, greater than 3. So greater than 9 divided by 3 means it is greater than 3. So now even if we take n is equal to 1, so the entire value under the square root is still greater than unity, and if n is more than 1, like 2, 3, 4, 5, etc., the entire value becomes definitely greater than 1. So since this entire value is greater than 1, so therefore we can say that sigma x multiplied by sigma px, so the product of uncertainty in position and the uncertainty in momentum, becomes greater than h cross divided by 2. Okay, so this is nothing but the Heisenberg's uncertainty principle. Okay, so in other words, the product of the two uncertainties would be greater than the Planck's constant h cross by 2 divided by 2. So this is one way of the statement. Another way of the statement is the product of these two should be in the order of h cross, okay, or should be at the order of Planck's constant. So you know what is the value of Planck's constant? So it should be at least in the order of h cross. Whenever the uncertainties of position and momentum, they fulfill these conditions, either this or this, so sometimes this can be replaced by greater than equal to, the same thing. So that then we can say that when these conditions are fulfilled, that the particle follows the quantum mechanical conditions. Okay, so that means it obeys the Heisenberg's uncertainty principle. So now let's take a little bit greater look, closer look about the Heisenberg's uncertainty principle. So from this, how can we say that if we want to measure the momentum specifically, the position becomes uncertain, or vice versa? So let's take a look from the mathematical expression that we have got so far with by a very simple approach. Okay, so what's that? So let's do things from this expression itself. So we have already written the uncertainty in momentum, all right, sigma px, which is n pi h cross by a delta px. So now look at this entire expression. Okay, so suppose we are very certain about the where the particle is. Okay, so where the particle is means the uncertainty in length a. So a means, so the particle can stay anywhere between 0 to a. So this length is a. All right, so the moment we locate the position of the particle over here, so we can say that to specify position means a tends to 0. Okay, because the length tends to 0, because now particle is fixed. So when a tends to 0, we can, if you can see here that sigma px tends to infinity. Okay, so the moment we specify location, its momentum becomes uncertain. All right, so it also like works in a reverse manner. Suppose you want to specify the momentum, right? So if we can measure specifically the momentum, so that means if we specify momentum, or that means if we specify px, so that means the px, or actually the sigma px, tends to 0, because uncertainty becomes 0 here. So when sigma px becomes 0, there is no uncertainty in momentum. This fraction tells me automatically that the length has to be infinite. So that means you cannot locate the particle. Okay, so forget about within this 0 to a. So you can never ever have any information about the position of the particle. Your length has to be infinity. So when its length has to be infinity, that means the particle is no longer confined in a one-dimensional box. Okay, so this way we have verified very simply that the underlying principles of Heisenberg's uncertainty theory, or Heisenberg's uncertainty principle, and everything we derived from this mathematical expression, which is the expression of sigma px, uncertainty in momentum for a free particle in one-dimensional box, is n pi h cross divided by a. All right, so this is the way we got a glimpse or got a feeling that how a free particle in a one-dimensional box satisfied Heisenberg's principle, uncertainty principle, and what is the uncertainty in position and momentum, how to calculate it, and then from the two uncertainties, how to verify that the product would be in the order of h cross, or greater than equal to h cross by 2. Okay, so now there is only one part left. What is that? So before we have found out that the average value of momentum for a particle in a box is 0. The question is there any physical significance, or is there any more information from this expression we can derive? Okay, so we will discuss a few more points regarding the average particle, the average momentum of a free particle in one-dimensional box becoming 0. So let's clear the blackboard and quickly discuss it. Okay, so now we would like to interpret the momentum, average momentum of a free particle in a one-dimensional box in this manner. So let's see that the psi nx is not an eigenfunction of the operator px, definitely, because the operator is pn, the px cap is minus ih cross ddx. If it gets operated on this psi nx, you see we are getting back to some cosine function, from sine function to cosine function, and this is definitely not an eigenvalue equation, and this value is definitely not an eigenvalue. So this means what? So this means that the particle, the free particle, does not have a definite momentum when it moves freely in a one-dimensional box. Okay. So, but whatever it is, its average momentum is 0. So now let's take a look a little bit inside into the this function, the wave function. Okay, so how? So let's recollect the Euler's formula about sine theta, so which can be expressed in the form of e to the power I theta minus e to the power minus I theta divided by 2i. So similar formula we have referred to our earlier in chapter 1, okay, while we are discussing about the general solution of some differential equations. Okay, so now if sine theta can be expressed like this, so then therefore I believe that the psi nx for a free particle in one-dimensional box, this one, can also be interpreted like this. So root over of 2a then multiplied by 1 over 2i, okay, and then whole multiplied by e to the power, okay, so I n pi x by a minus e to the power minus I n pi x by a. All right, so now we get an interesting expression. So this is our psi nx, that is the wave function for particle in a one-dimensional box, which is not an eigenfunction of the momentum operator. But interestingly, it can be expressed something like this, exponential something minus e to the power exponential something. So here I would like to draw your attention that if we apply the momentum operator, that is px cap, on a function, the function is something like exponential e to the power plus or minus I n pi x by a. Okay, so this is the function, exponential function e to the power plus or minus I n pi x by a. If we apply our same px, that means this is nothing but minus ih cross ddx. Okay, so what we get here is plus or minus n pi h cross divided by a e to the power plus or minus I n pi x by a. All right, so we actually get that, this expression. So now this function is an eigenfunction of the momentum operator px, and the entire equation is an eigenvalue equation, and we get the two eigenvalues plus or minus n pi h cross by a. All right, so but you see our original wave function contains this term e to the power I n pi x by a minus e to the power I n pi x by a. Okay, so here again we see this n pi x by a. All right, so it comes over as the power of an exponential function, where this is a part of an eigenvalue function or eigenfunction. So therefore, we may try to interpret or try to think the relation of these two things, that perhaps our wave function is a superposition of two momentum eigenfunction, okay, with eigenvalue which is plus n pi h cross by a and minus n pi h cross by a. And since those two eigenvalues are acting in the opposite manner, since those signs are opposite, the average value comes out to be 0. All right. So if you have a difficulty to follow my words, then I try to write whatever I stated, so it might be little helpful for you. Okay, so just let's do it. So I wrote here in words that psi nx can be thought, that means our wave function for particle in a box can be thought to be the superposition of two momentum eigenfunctions, one with the eigenvalues, means one with eigenvalue plus n pi h cross by a and another with eigenvalue minus n pi h cross by a, averaging out to be 0. So that means perhaps if there exists a particular eigenfunction for momentum, that is e to the power this, then our psi nx can be thought to be a superposition to eigenfunctions, okay, with two eigenvalues plus this and minus this, so that the average momentum becomes 0. But here once again I would like to remind you that its average momentum is 0. That doesn't mean the entire momentum is 0, because the particle is not stationary. Okay, so you should remember that. And before we finish, just one more point. So where else did we see these two values, plus n pi h cross by a and minus n pi h cross by a? I can tell you, we just saw that a little while earlier. Okay, so let me show you how. So let me erase this part and let me draw your attention about the average kinetic energy. So what is the average kinetic energy for a particle, for a free particle in one-dimensional box? So it can be represented as pxs square by 2m average. Okay, since this is a constant value, so we can take this thing out of this average value, so it becomes 1 over 2m average of px square. So the thing is, what is the average of px square? We just found out a little while earlier that this is n square pi square h cross square by a square, isn't it? We have definitely calculated this. So this is the average kinetic energy and it takes up the value of this. All right, but if I have asked you what is the square root of this average kinetic energy, all right, so the square root of average Ke, it becomes root over of this entire value. All right, so when you take the root over of this entire value, you will see definitely the square root would contain this part, that is the two roots of this plus or minus n pi h cross by a, and there are some constant, but we are neglecting this. So we see when we take the square root of the kinetic energy, or basically the square root of px square average, we see there are two values, n pi h cross plus n pi h cross by a and minus n pi h cross by a. So therefore we see that there are two definite momentum eigenvalues getting superimposed for a free particle in one-dimensional box, and the result of which is 0. All right, so this is all about chapter 3, the Schrodinger equation, and some of its simpler applications in some systems. So I hope that you have been able to follow this, and I recommend you to study the textbook in detail for a for better understanding. Okay, so we meet next time for some more tutorials, and we can proceed to our next chapter, which is chapter 4, some basic postulates of quantum mechanics. So till then, goodbye.